we are going to look at processes that govern the operation of a laser. So in terms of matter, I make an approximation. Let me just look at a two-level atom as a model for the matter. And for light, we will look at a monochromatic or monoenergetic beam of photons having a specific frequency h nu. For simplicity, we will say that these photons, the electromagnetic radiation, is on resonance with the atom. That would mean that if I associate a frequency nu and hence the energy h nu with a photon, this matches very well with the frequency which is that of the atom. That is, in the atom, I have got two states. I'm representing the ground state by the letter 1 and the excited state by letter 2. So these are my two states. So as you can see, this way of representing the atom is with respect to the energetics of the atom. This level is corresponding to a level 1 energy corresponding to the electron in the atom at energy E1, and this is corresponding to the electron with the energy E2. So the atomic energy is given by E2 minus E1, which is basically h times nu 1 2, and I'll come in with a photon whose frequency is nu, and my claim is that the photon energy is same as the atomic energy. So when I come in with photons that will interact with such an atom, multiple things can happen depending on where the electron is. So what I will do is basically look at the most dominant processes that are pertinent for the laser operation. There are very many multiple things that can happen, but we will not look at them in this context. In the context of laser, we will simply focus on things which are most pertinent. So what I will do is basically classify two kinds of processes, and one of them is I will call as radiative, right? And the other one is obviously non-radiative. So let's look at the radiative process. You have heard of something called spontaneous emission. So this is the first process that I'm going to describe. What I have here in spontaneous emission is I have the atom, and it so happens that the electron in the atom is in the excited state. I'm representing that electron with a little dot here, and the electron is in the excited state. So in spontaneous emission, what happens is that you have the electron from the excited state comes down to the ground state, right? It comes down, and the electron at the end of the process is there. Not just that, this energy which it loses is actually given out in a random direction, and this photon, this energy which is quite close to the atomic energy, is what is emitted. Note that this photon carries a momentum k. It has the frequency, it has energy h nu, and this is in a random direction. It's momentum k, so this emission is in the random direction. So by the way, this is precisely how most of the terrestrial sources that we see, for example, a tube light to a bulb, all of these involve essentially spontaneous emission. The second radiative process, which I want to talk about, is something that is contained in the acronym of the laser itself, right, which is stimulated emission. So in stimulated emission, again, prior to the event, which is stimulated emission, the electron is in the excited state, and now what is happening is that there is a photon that comes in. The photon energy is quite close to the atomic resonance energy, and this photon with wave vector, for example, k, comes in. So at the end of the process, what you have is the electron in the ground state, and you have two photons which are identical to each other, which are having the same momenta k. So you see, unlike the spontaneous emission process, in the stimulated emission process, you have two identical photons being produced at the cost of the atomic energy. Again, a note that these two particles are exactly identical in the quantum mechanical sense. That is, you cannot formulate even a Gedanken experiment, a thought experiment, where you can determine which one was the stimulating photon and which one was the stimulated photon, because both the photons are exactly identical. They have the same polarization, they have the same momentum, and they have exactly the same energy. For all practical purposes, they are exactly identical. And you do know that the making of the laser is centrally dependent on this process being dominant among all the other processes. Now let's look at the third radiative process, which I am calling as absorption. So in absorption, what you have is the atom is in the ground state. So again, a small note that I would sometimes use the phrase that the atom is in the ground state, by which I mean that the electron in the atom is in the ground state. And keep in mind that we are going to always deal with single electron atoms. These are atoms which are hydrogenic kind of atoms. That is, you have only one electron in the uh, outermost shell, which is what is involved in all these radiative as well as non-radiative processes. All right, so in absorption, the electron in the ground state, and then you have the photon of energy h nu, again momenta k, which is coming in, and at the end of the process, what you get is that the electron takes away the energy of this photon and goes to the excited state, and this photon energy is now stored in the atomic excitation. Right. So these are the basically three radiative processes that are important for the operation of a laser. Now I'm going to look at non-radiative processes. So among the non-radiative processes, the one that uh, we will keep using is also plays a very important role in making of the laser is basically the notion of pumping. As you recall, among all the processes that we described above, it is a stimulated emission that we want it to uh, play the most dominant role. And clearly, what one required was that the atom should be in the excited state for stimulated emission. So one needs to prepare the atom or prepare the electron to go from the ground state to the excited state, and that is something that we achieve by using non-radiative pumping mechanisms. So let me just indicate that pictorially in the following fashion. So in this, what you do is you have the atom in the ground state. You add energy. This energy is not necessarily radiative. For example, inside an electric discharge, you can have accelerating electrons which are carrying kinetic energy, and these accelerating electrons collide with the active atoms of the laser, and they excite these atoms to the excited state. So this kinetic energy is converted into internal energy of the atom. That is the kind of process that one is looking at. In a chemical laser, it is a chemical reaction that provides this energy. So what you get is basically now the atom in the excited state, right? And this energy which has been provided is used to basically uh, change the internal energy of the atom. This is also equivalent to the word pumping that we will keep using repeatedly in the laser operation. This will play an important role in creating this population inversion that you might have heard when people talk about laser. The word population inversion comes from the fact that you have a collection of active atoms, and what you would like is a large population of these collection of atoms should be such that the electron should be in the excited state, and that is what we call as population inversion, because in thermal equilibrium largely the electrons will stay in the ground state, right? So I'll come to this notion of a thermal equilibrium in just a moment. Now let's look at the second non-radiative process, de-excitation of the non-radiative kind, non-radiative de-excitation. So herein what you have is you have put in energy in the excited state, right? So the electron is in the excited state, and what happens is the atom comes down to the ground state and releases this energy, and this energy is essentially lost as heat. So for example, you are looking at a solid state laser. This energy might be lost in terms of phonons, which is basically the energy which is contained in the crystal, vibrations associated with the crystal that is holding the active atom. So you see that this energy is lost in a non-radiative fashion. There is no photon going out in a particular direction like we had for spontaneous emission. Yet this energy is lost, uh, and the atom comes down to the ground state. One important note, which is in thermal equilibrium, let us be very clear that you would find most of the atoms are in the ground state. Actually, in thermal equilibrium, the electron distribution follows something called the Boltzmann distribution. So, for example, the probability of finding the electron in the excited state divided by the probability of finding the electron in the ground state would actually go as exponential minus E2 minus E1 by kBT. Think of it pictorially. So let's say that this is my level E1, this is corresponding to level E2, and now if I look at the population distribution, you will see that there is a exponential dependence of the population. That is, exponentially small amount of population resides in the excited state, whereas this exponential dependence is largely governed by the temperature T and the energy difference between the two states, E2 minus E1. So, for example, at room temperature, where the temperature is 300 Kelvin, one can correspondingly calculate the thermal energy, which I told you is 1/40th of an electron volt. The energy difference that is in the laser, we are looking at E2 minus E1 of the order of 2.5 electron volt. So you can clearly see that you would get this fraction as so, which is e to the power of roughly minus 100. So you clearly see that extremely small population is actually there in the excited state. So in thermal equilibrium, you would see that all the population largely remains in the ground state. Whereas when we want lasing to happen, we are creating this very unnatural situation wherein you would like that the ground state has got less population and most of the electrons are in the excited state, creating this rather funny distribution, which is certainly non-thermal. That is, if things are at thermal equilibrium, this would relax back. This is where spontaneous emission will take over and you will have atoms coming down to the ground state so as to come back to the the thermal equilibrium situation. One is literally creating an inversion in the population. In very early times of laser, people used to associate this with sort of a negative temperature. Okay, just because you have completely opposite distribution of the exponential, not really correct, but then that is a kind of notion that one would have. So again, let me quickly recall. What you have is variety of processes that can happen with the atom. Parts, one is radiative, spontaneous emission. For example, if you put the atom in the excited state, there is a lifetime associated with the excited state, and the atoms will typically come down. For example, the typical lifetimes of excited states will be about 10 power of minus 8 of a second in atoms, uh, and in molecules it's even faster. So you see that you will come down to the ground state, and this giving up a photon in a random direction. In contrast, in the stimulated emission, what you have is an incoming photon which is actually stimulating the electron which is in the excited state and producing two identical photons. You also have the other process where the photon energy is absorbed by the electron and the electron goes to the excited state. And then you have the non-radiative processes wherein you put in energy to take the electron to the excited state in a non-radiative fashion, implies, for example, collisional energy, uh, chemical energy. You also have the non-radiative de-excitation, that is, the energy in the excited state may not necessarily always give out a photon, but could lose energy in a non-radiative manner, thus not being able to maintain the population inversion that you have generated. Right. So these are the main processes that we need to keep in mind, which are going to play important role. So what I will do next is to come up with a simple model for the laser. It kind of captures the strong interaction between light and atom. Most essential aspects of the laser is captured by this model. It is discussed very nicely in your textbook, Lasers by Melloni and Eberle. What this model provides is a insight into the nonlinear interaction between light and atoms and operation of the laser and creation of this lasing photons.